Welcome to Yaka Digital Network. Look at this split screen. On the left, we have coarse salt crystals dissolving in a pot of water over high heat. On the right, a plastic bottle warping and melting near a simple flame. Why does the salt survive the heat and mix with water, while the plastic melts and repels it? This contrast is a direct result of chemical bonding, the invisible forces holding atoms together. These internal connections dictate how every single material behaves in the real world. Understanding these forces requires a look at the atoms themselves. Pay close attention to the outer valency electron shells, as well as the protons and neutrons in the nucleus. The way these electrons interact is what creates the bond. We group these atomic interactions into 3 specific models: 1. Ionic, 2. Covalent, and 3. Metallic. By understanding the rules of these 3 bonds, you can predict the physical properties and everyday uses of almost any material you encounter in Uganda. Let's start with this 3D model of sodium chloride, or table salt. This is an ionic bond. It forms when a metal transfers electrons to a nonmetal. The result is a massive repeating 3D lattice, where a rigid grid of positive and negative ions is locked firmly together by strong electrostatic forces. Because these electrostatic forces pull intensely in every single direction, pulling the ions apart is difficult. It requires immense heat energy to melt this lattice. So what happens if we wire this strong, solid structure to a battery and try to pass electricity through it? Nothing happens. Electricity requires moving charges, and in this solid lattice, ions are trapped in place. But watch this. When we dissolve the salt in water, the grid breaks apart. The ions float freely, and the bulb instantly lights up. The incredible structural strength of an ionic bond is exactly what prevents it from conducting electricity, until that structure is physically dismantled. Our second model is covalent bonding. Here, we see 2 nonmetal atoms moving close together. Instead of transferring electrons, their outer shells overlap to share a pair of electrons, stabilizing them. But covalent bonds create 2 completely distinct macrostructures. On the left, we have a simple molecular structure, like a small cluster of water molecules. On the right, a giant covalent structure, like the massive continuous network of carbon atoms in a diamond. Focus on the water for a moment. The covalent bonds inside a single water molecule, connecting the oxygen and hydrogen atoms, are actually extremely strong. However, the forces between the separate individual water molecules are very weak. It takes very little energy to break these apart, allowing the molecules to slide past each other fluidly. This is why water is a liquid at room temperature. For covalent materials, the internal bond type doesn't give you the whole picture. You have to look at the macrostructure, whether it's a giant network or isolated simple molecules, to know if the material will be a hard solid or a flowing liquid. Our third model is metallic bonding. The materials we use every day, like iron roofing sheets and the copper wiring shown here, rely on a completely different system. Inside this copper wire, the positive metal ions sit completely stationary. Meanwhile, their outer electrons break free and drift throughout the material, creating a constantly flowing sea of electrons. Let's test this concept. Here is a lab circuit set up above a beaker of sugar. Sugar is a simple covalent molecule. Pause the video and predict, will this bulb light up? The bulb stays completely dark. Because covalent molecules share their electrons tightly within the individual molecule, there are no free charges available to move through the water. The rule is this: whether you are dealing with a sea of metallic electrons or dissolved ionic particles, electrical conductivity always requires free-moving charges. In your practical exams, you will need to deduce bond types from lab properties. We can do this using a straightforward logic flowchart, starting right here. Step 1. Does the substance conduct electricity? If yes, look at its state. A solid conductor is metallic. If it only conducts when dissolved or molten, it is ionic. Step 2. If it does not conduct electricity, check the melting point. High heat resistance points to a giant covalent structure, like diamond or sand. A low melting point means it is a simple covalent structure, like sugar or wax. This summary table maps exactly how these properties align with ionic, simple covalent, and metallic bonds. Take a screenshot now to use for your exam preparation. Thank you for learning with Yaka Digital Network. For more detailed lessons, quizzes, and resources, visit our website today. By understanding the invisible architecture of atoms, you gain the ability to accurately identify, manipulate, and utilize the physical world around you.